Welcome to Pre-Calculus Unit 2, Lesson 15. Our learning target for today is solving logarithmic equations. So in lessons 12 and 13, we practiced simplifying logarithmic expressions. Now we're going to use those simplifying skills to actually solve equations. So when you're solving log equations, it is pretty much a 5-step process. So step 1 is going to be using log rules to isolate the logarithm. And by that, I mean you should have an expression that looks something like this. Log base b of a equals x. It should match standard form. So you may need to combine some logs using the addition rule or the subtraction rule. You may need to take care of some exponents using that coefficient rule. So that's where our skills from lessons 12 and 13 come into play. Once you have it in standard form, you can convert to exponential form. So log functions and exponential functions are inverses of each other. So if we're starting off with a log equation, we're going to use exponential form to solve it. Once you have an exponential form, you can evaluate the exponent. So this b to the power of x should come down to some real number. Then you can solve the resulting polynomial. And the last step that everybody likes to forget about, check for extraneous solutions. And the way you check for extraneous solutions is that the argument of a logarithm must be positive. So when you're checking for extraneous solutions, what you really need to do is check that when you plug in your x value, substituting for x gives a positive argument. Because the log of any kind of a negative argument is undefined, and that would give you an extraneous solution. So let's try some examples. Let's see what this is. Right here, I've got log base 2 of 4 plus log base 2 of 2x equals 4. So my first order of business here is to use my log rules to combine this into a single logarithm. I've got two logs with the same base that are being added together, so I need to multiply those two arguments. So I'm going to be multiplying the 4 and the 2x. That will become log base 2 of 8x equal to 4. And now I should be matching my standard logarithmic form. Log base b of a is equal to x. And indeed I do. My argument is 8x, base 2, exponent 4. So once we've got it all in standard form, we can change it over to exponential form. That's using the inverse function. So this will become an argument of 8x is equal to 2 to the power of 4. And now, like I said, we've got a real number here. This is an exponent that we can evaluate. 2 to the power of 4 is simply 16. So right now, I've got 8x equal to 16. Well, that's easy math. Divide both sides by 8, and we got x equal to 2. Now, I should go back and double check my arguments here that I'm not getting any kind of a negative argument. So I do log base 2 of 4. That doesn't even have an x in it. But if I do log base 2 of 2x, plugging x in for that, it will be 2 times 2, or 4. That's a positive number, so we are good to go. This is a real solution, not an extraneous one. X equals 2. Next one here. I have 5 times the log base 3 of 7x plus 6 quantity squared equals 20. So here I need to isolate the logarithm. I need just the log base 3 of 7x plus 6. So right now I've got this 5 in the way, and I've also got this 2 in the way. Well, lucky for me, I know about the exponent rule. So this exponent of 2 can go down here and join with the coefficient. So 5 times 2, that becomes a coefficient of 10. So 10 times log base 3 of 7x plus 6 equal to 20. So now the exponent is gone. And to get rid of this coefficient of 10, I just need to divide both sides by 10. So now I've got log base 3 of 7x plus 6 equal to 20 divided by 10, which is 2. So again, now I match my standard form. I've got a base, I've got an argument inside the parentheses, and I've got an exponent. So once it's in standard form, we can use the inverse function, change it over to exponential form here. So the logarithm is gone, and we just have 7x plus 6 equal to 3 to the power of 2. Evaluate that exponent. 3 to the power of 2 is 9. So 7x plus 6 equals 9. Subtract 6 from both sides, and we get 7x is equal to 3. Divide both sides by 7. X equals, and we can do this in decimals, 3 divided by 7, 0.429. And now it's always good to double check that if I plug my solution back in for x, that I'll still have a positive argument. So if I do that, 7 times 0.429 plus 6, that's equal to 9, which is a positive number, so we are good to go. This solution is real and not extraneous. Two more examples here. This time I have log of x plus log of x minus 3 equal to 1. So we've got two logarithms here with the same base. They're both base 10 being added together so I can combine with multiplication. This becomes log of x times x minus 3, or x squared minus 3x. I'm going to go ahead and distribute. That is equal to 1. So now I've got my standard form. I've got my base 10, my argument in parentheses, and my exponent of 1. So I have here, changing it over to exponential form, that argument x squared minus 3x is now by itself equal to base 10 to the power of 1 is just 10. So x squared minus 3x equals 10. Now this time, we no longer have just a linear function. We have a quadratic, but we know how to solve those. I'll subtract 10 from both sides. X squared minus 3x minus 10 equals 0. That's a quadratic, so we should try to factor it. Well, multiplies to negative 10 and adds to negative 3. Well, that will be x minus 5 and x plus 3 equals 0, which gives me solutions of x is equal to positive 5 or negative 3. So when you have two solutions, it's especially important to check whether one of them is extraneous. If I try to go back in here and take the log of 5, that'll work out just fine. But if I try to plug in negative 3 for x, now I'm taking the log of a negative number, and that's undefined. That tells me that negative 3 is an extraneous solution. So my real solution set here is only x equal to positive 5. So when you're double checking, make sure that you're not taking the log of something negative. I will do one more example here. This time we have log of 10x minus log of 2 equal to 2. So the rules of logarithms here, I need to get rid of the two separate logarithms. I need to combine them into one. So I will use division. This becomes log of 10x divided by 2. And 10 divided by 2, that's a fraction we can simplify. This ends up being just the log of 5x equals 2. So now I've got it in standard form, base 10, argument 5x, exponent 2, so we can change it to exponential form. Argument 5x is equal to base 10 to the power of 2. Evaluate the exponent. 10 squared is 100. So 5x equals 100. And then to solve for x, we just have to divide both sides by 5 and end up with x equals 20. And for this one, if I try to plug it back in for my argument here, 10x, 10 times 20 is going to be 200. That's a positive number, so I know that this is a real solution. X equals 20. So moving on to our next step, here, problems 5 and 6. I'm going to pause the video, let you guys try these on your own, and then we'll talk through it. So thus far in this first problem, I have taken the coefficient, the exponent here, and combined it with the coefficient to get 15. And then I've divided both sides by 15 to get log base 4 of 2x equal to 3. Now that this is in standard form, we can convert it to exponential notation. So the argument of 2x is going to be equal to the base of 4 raised to the power of 3. So that will give us 2x equal to 64. Divide both sides by 2 and we'll get x equals 32. And if you plug that back in, you'll end up with the log of 64, which is a positive number. So that is a real solution. Now for problem 6. Some people might get a little thrown off by this ln, so I don't want you to be confused if you see a natural logarithm. We first need to isolate the log, same as always. So I'm going to take this exponent and turn it into a coefficient. This will be 2 times the natural log of x plus 1 equal to 2. And then I can get rid of it completely by dividing both sides by 2. Now I have the natural log of x plus 1 is equal to 1. Now, don't forget that natural log means the same thing as log base e. So I've got a logarithm here with base e, argument x plus 1, exponent 1. So we can change this over to exponential form just like any other problem. So the argument is x plus 1. The base in this case is the number e, and the argument, or the exponent, is 1. So here you'll need to use your calculator. E is the button just above the division symbol. So if you do second divided by, that will give you E in the graphing calculator. So second divided by gives you E raised to the power of 1, 2.718. So x plus 1 is equal to 2.718 here. And then to get x alone, subtract 1 from both sides. X is equal to 1.718. That is a real solution. So anytime you need the number e in the calculator, you're going to press second and then divided by. And that will give you the number e anytime you need it. So these last two problems, I'm going to pause the video. You guys try them on your own and then hit play just to see the final answer and check whether you are correct. And here are your solutions for problems 7 and 8. So here, you should end up for problem 7 with x squared equal to 256. So if you square root both sides, you'll end up with x being equal to plus or minus 16. But if you look especially up here at this second logarithm, log base 2 of x, we clearly can't plug negative 16 into that without it becoming a negative or undefined logarithm. So negative 16 is extraneous. The real solution is x is equal to positive 16. For problem 8, once you combine everything and change it over to exponential form, you should end up with x squared minus 3x minus 18 is equal to 0, which factors to x minus 6 and x plus 3. So your possible solutions are going to be positive 6 and negative 3. But again, looking at the second logarithm, if I try to plug 6 in for x, that works just fine. But I cannot plug a negative number into a logarithm. So negative 3 is an extraneous solution. X equal to 6 is your only real solution. So that is solving logarithmic equations in a nutshell. You should be ready now for my participation check, and then we'll move on to exponential equations.